what we would really like to do, it's either run as many simulations as possible and get later on a machine learning model to understand what is the effect of all the changes that we're doing into the model, and reading some variables and see what is the effect of those changes into those variables. In this case, for instance, the history matching quality, or the water cut, for instance. And that's what we want to achieve. So what I have done is use experimental design. There is a question here. Is the objective function limited to a few wells, or should we implement it for all the wells? What is the recommended practice? Yeah, that's a very good question. You can do multiple level objective function, and whenever you have data, real data that you have measured, and your simulator is able to come up with a result for that data, piece of data, you should write a objective function. So the well level is obvious because you are, well, it's obvious in some fields where you are actually measuring the production per well. Of course, you have issues where you have data back allocation, production back allocation, and that is a major issue with history matching, because depending on the quality of the back allocation, you have a lot of error in the. If you have a lot of error in the back allocation, there is just so much that you can do with the quality of the history matching. But having said that, you may have a PLT. You may have, like the sessions that we have done before. If you have production logs, you have pressure data from the wells. Let's say you have a RFT, or in the sessions that we have done previously, where you have MWD data as you drill, and you have a pressure reading. The simulator can come up with that pressure reading, and you can use that as an objective function. So the other thing that you can use, it's now abstracting from the data at well level or completion level. If you have data at completion level, you can have data at group level. You want to group quite a few wells, and then do a kind of a sum of objective functions and see the quality of history matching for a particular block or particular production horizon. You can also do that. And of course, you should always do a field level history matching. You should always have those on. So the more, the merrier, and it's up to the capability that you have to really analyze all that data. Because the problem with the history matching is that when you start to add all this stuff, then you start to have a lot of data to analyze, and you really need to have put together the right tools to analyze your results. You have to put together dashboards and so on. As one of the images that I have here is one of those dashboards that we have put together in the past, which is a water cut objective function, bottom hole objective function. You have a ranking of the models. So you have quite a few metrics that we put in those dashboards, and it's also a very good communication tool to explain to a geologist or the geophysicist even what you see that is missing. And I'll show you in a bit what in this particular data in norm, we can take it as an analog to other fields, and you could see how quickly, even if you're changing drastically a lot of parameters, you can see that the history matching ranges are not really covering the production data that you have observed in the reality. So you may actually have to go back to a geologist and change your model in a more drastic way. Okay. Right. So another question. Oh no, that's a dashboard that I have built in past projects, and that's more in-house, something that I have built in either Spotfire, mainly Spotfire. And it can be built in Python, probably using Dash. But yeah. nothing that objective function is not something that come off the resin side doesn't calculate the objective function. So you need to implement these functions by yourself. Or you need to use a tool like MIP or Petrel to come up with the objective function calculation. Okay, so moving on, and while we move on, this is still running. That's your case. I'm going to move into experimental design. So experimental design or design of experiment is a very optimal way to sample your cases or to generate a matrix of cases where you want to test different scenarios or different input variables into your models. So why we want to do this? So let's take DCA. So we want to, if I want to do a sensitivity analysis on a decline curve analysis, for every well that I have, it probably takes me less than a second to run a decline curve analysis. And even if I have to fit some data and then I have some uncertainty on the data, it's very fast to fit the decline curve analysis and ARPS equation and come up with a range, deviation, a mean of your coefficients. That's super fast. 1 second up to 5 seconds max, perhaps, and I'm exaggerating here. Now, this model, as you can see here, this model is still running. So we have one model, only one model. I have submitted just one model. We generated two, but I have submitted only one, and it's still running. And it will take 15 minutes more to run. What happens in the reality when you're executing these reservoir simulation projects, you have models that could take, if you're lucky, the models could take 1 hour or 2 hours to run. And but there are models that, for instance, when you're talking about compositional models where you need to characterize gas condensate effects or condensate dropout around your wellbore, or you have thermal models such as steam injection, SAC-D, and so we're talking about models that could take up to a day or more than a day to run. There are models that needs quite few million cells as well, and simulators are getting better and better in that arena. But you might be able to get one simulation run per day in those extreme scenarios. And of course, the idea is to put together models that are practical, that you can evaluate. I mean, 1 hour, it's not so bad, especially if you finish your day, you submit your cases, and by next day you have quite a few models. Then that's very productive. In the morning, you have a lot of results, which is what I have done more or less here. Like I submitted some cases yesterday, and then I'm actually going to show you some of the history matching quality. So why we use experimental design? Because we want to limit the number of scenarios that we would like to run. We want to change the input, but we don't want to run thousands of cases. We don't have the capability to run thousands of cases, either because you have a limitation on the computing power, or you have a limitation on the license of a simulator that you are using. Okay, those two are probably the two bottlenecks that you will have with your simulator. So some things that you can do, it's exactly that what I was doing previously in this example. I can come up and start to do some sensitivities by myself and just create my own sensitivity analysis. Just create a few scenarios, add this to the table, generate models, run the models, then load it in resin side and have a look what is going on. Is that efficient? Perhaps not. So that's why you have the design of experiment or experimental design, which is a more economical method, more optimal method to evaluate the simulation results. So we want to study, in this case, in this particular case, we want to study the history matching quality of a model. But if you're doing an analysis on the prediction, perhaps what you would like to see is how much is the cumulative production affected by all these parameters. And it's pretty much the same problem. It's the machine learning problem. We have been doing this in reservoir simulation for quite a few years. The only thing that is coming along, it's probably new techniques that probably can be a bit better than just simple linear regressions. So it's what we want to do, and what do we know? It's very important to understand. In this case, I frame a project, I frame a problem based on the understanding of let's say, this reservoir. I frame the problem on the understanding of the connectivity. I want to check what is the structural connectivity impact in the characteristics of a history matching. And I want to check what is the sensitivity on the connectivity of the different stratigraphical zones in the quality of a history matching. And I want to run as a decent amount of simulations that can come with certain results. So these experimental design methods, the ones that I have listed here, full factorial, fraction factorial, so they have been, or at least from the list from this point downwards, they have been, let's say, designed with a mathematical, let's say, in the space. If you think about 2 dimensions, it's very easy to see what are the combinations that you want to run. So I want to run the extremes, and I want to run a mid factor. So if I have 2 variables, it's very easy to see that I want to run high, high, low, low, high, low, low, high, and probably mid, mid. Okay, that is an experimental design. We know that I'm evaluating the whole space of the whole space of uncertainty of these two variables, but it's not going to be an expensive experiment. Now, the problem here is that we have, in the particular example that we're running, let's see how many variables we have here. The problem here is that we have here 14 variables. So that we're talking about a multi-dimensional problem. So we have many dimensions, and the combination of those can be quite a lot. And we will see that in a second. So the first thing that you may want to do is, I want to do a full factorial. I want to test everything, all the highs and all the lows in all the potential combinations of all the cases for all these variables. Okay, and let's see if that is a sensible strategy. Then there are fractional factorial, which is, as the name states, is just a fraction of the full set of experiments. And there are some more experiments that are cheaper, like Plackett-Borman and box-pecking, and the optimal space filling. So let's go to the full factorial. Let's say in the scenario where we have 4 variables, and I want to test -1 and 1. In this case, it's a low variable. And let's talk about connectivity, for instance. We want to test if the fault is sealing or if a fault is open. That's it. We don't want any value in the middle. We just want to check those strings. Sealing and conductive faults. So what you have here is you have a fault A, fault B, fault C, and D, and you have all the potential combinations of all those faults. Now let's see in this example, and let's start to work on experimental design here. And what I would like to do is first, I'm going to import the library PyDOE2. And I'm going to go for the expensive design. So I'm going to go for the PyDOE2. Let's see what I have here. I have a full factorial. And if I go into the documentation, I just need to provide the number of variables that I have in here. So actually, if I run this again, I know that all variables is. Hello, can you hear me?
We can hear you, Alejandro. Yeah.
Excellent. Thank you, Victor. So, okay, we want all these variables. And if I check what is my n is a total number of variables. So I'm going to put n here. And let's call this DOE. This is a DOE full factorial 1. I'm going to call it like that. And let me see what I get. Oops. So here I have -1, -1, -1, 1, 1. I have a combination. Actually, what I'm going to do is put this in a data frame and put the name of the columns. So I can do, I can use pandas, and let's call this data frame underscore DOE full factorial. This is a full factorial. And I'm going to put it in this data frame. I'm going to put it here. The name of the columns is going to be equal to all variables. And let's see what we have in here. Okay. So do you think that is it practical to run that matrix with these extreme values, high and lows? Remember, in this case, -1 represents for, we have to convert those, and there is a step that we will do in a bit. We have to represent -1 as a extreme ceiling fault and 1 as a conductive fault. Do you think that we can run this experiment? Yes, no, and why? How many cases do we have there? Yeah, good luck with running the cases. Yes. So how many cases we have? We have 16,384 cases. And as you can see, the one that we submitted a few minutes ago, it's still running. So there is no way in which we can, we are able to run this full factorial design. So we have to go to a more, let's say, a cheaper design. So
Alejandro,
yes.
Excuse me, a question. In this case, all the cases are run in series, or there is a kind of parallel simulation that you can have here?
You can run in parallel, and you can generate your a batch file. And in the batch file, you can have a routine in Python, or let's say a LSF manager of queues that picks wisely or select how many simulations you can run. If you have a cluster available, you can run a lot of those cases in parallel. In this particular case, let's assume I have only my machine, and I can run in my machine 3 cases at a time. When I run 4 cases at a time, and I can see that they all start to run slower. So there is almost like no improvement in terms of speed, or there is a performance impact on the speed when I try to run more than 3 cases at a time. And obviously as the model get more complex and you don't have the resources, then obviously parallel, it's almost like, you know, when I mean parallel, it's running cases at the same time. I'm not talking about domain decomposition, which is splitting the domain of a simulation model in different domains and trying to resolve them in different CPUs. That's another topic.
Okay, thanks.
Okay, so this is not feasible. So let's go to the next exercise, and let's do something a bit more rational. No? Let's see if we can do a fractional factorial. So fractional factorial, it's a fraction of a whole full factorial, and there are different levels of fractions. I'm not going to go to the details, but basically instead of having 2 to the 64, you have just a fraction of a 2 to the 64, or 2 to the 64 runs. You have a fraction of those if you have 6 variables with only trying low and high. I'm not talking about trying mid, low, and high. If you try mid, low, and high, we're talking 3 to the 6 if you have 6 variables. In our case, we have 14 variables. So what if I go straight to the design chart for a fractional factorial? So if you see the full chart, this is at the top. It's a number of factors, variables, input variables, features, however you want to call it. And this is a number of runs. So if you want to include 10 features or factors with low and high, and you want to have, I don't know well, let's take the 7 factors, and you want to run low and high with all the combinations, that's a full factorial, it will give you 128 runs. So the resolution, it's you have in here, you have like a 4:3 resolution, and you can control that in Python. So in PyDOE, what I'm going to do, it's actually, I know that the number of experiments wouldn't change. So I'm going to call this DOE fractional factorial. And I'm going to run from the library, a fractional factorial by resolution. So if I see the documentation, I can pass a number of factors, features, input variables, whatever you want to call it, and the resolution. So I'm going to run it at the lowest resolution. So I'm going to pass n, and I'm going to run it at the lowest resolution, which is, in this case, the resolution goes an increasing factor. So resolution 3, it's 1, resolution 4 is 2, and so on. So if I run that, and let's create a data frame as we created here at the top. DOE fractional factorial. And let me call this fractional factorial 1, just in case we want to change it later on. And this is fractional factorial 1. Oops. Let's see, 2. Okay, so we have 256 run. But still it's it is a very high number to run. So I think actually this reduces the resolution, and you can see that by increasing this, actually we're decreasing the resolution. So it's inverse. It's inverse actually. So we have -1, 1. You have a bit of a combination of all of those. Okay. So now let's imagine that I don't want to do this experimental design. This is a full factorial design. Is not possible in this case. And then a fractional factorial design is feasible with low resolution. I have 16 cases, 15, actually 16 because this index is 0. And we'll see if that is enough when we will run the machine learning, because what we may find is that it's not enough. And we will see that later on. So if I want to run that, there is something else that we need to do. Can I run this as it is, this table as it is? No, in fact, we cannot. We cannot run it. And I have a small function that could help us to scale these values from -1 and 1 into something that is meaningful in terms of connectivity. So I'm going to add this to my, let's call this, these actually are my useful functions. Okay, and I'm going to input this is detect all the variables. So this function that I put here is a log scaler. It just takes a minimum maximum value of the input that I want to scale, the new minimum and the new maximum. It takes a value and it scales that table. And the way I have put it is it goes from 0.0001 up to 1. So pretty much a fold that is completely sealed up to a fold that is fully open. And I'm actually going to call this, instead of fold log scaler, it's a connectivity log scaler. And this is quite useful for connectivity because you want to really test your connectivities in order of magnitudes. You don't want to take a transmissibility multiplier and try 0.5, 0.6, 0.7. What you really want is to test 0.01, 0.001, 0.01, 0.1, and 1. So that's the kind of a magnitude that you want to test. And with this connectivity log scaler, if I run this function, I'm going to use this the same matrix here. And what I'm going to do is where's my log scaler? Oh yeah. So I want to apply the log scaler to every column. So I want to apply that log scaler to this data frame. Let's call it scaled. I don't want to run with the one above. I want to run with this one. And for this, I can use a lambda and apply map. So I want to apply a function to all these columns. And let me see. I'm going to use a lambda, which is a sort of an in-place function. Well, Ankit, that's the first step. Ankit asked if we have reduced the cases from 16,800 to 15 cases. The answer is, I want to run only 15, perform regressions, and then I keep adding some more cases to the backs. And then I will try to, let's say, enrich my knowledge of the knowledge of the sensitivities by adding more and more cases. Okay, I will show that in a bit. So I'm going to do lambda, and with the lambda function, I'm going to pass a variable x, and this connectivity log scaler, what it does is I have to provide a minimum value, which is in this case is 0, 4, which is almost like what is the resolution of a log, 1, and I want to pass the x value. So if I apply that log scaler and produce this new matrix, let's see what we have. oops, name MP is not defined. Sorry, I need to import NumPy. Yeah, this is using NumPy, and it's using the power, and then divided everything by 10. So kind of a inverse of the logarithmic. There we have it. Now we have the transmissibility multipliers that we want to use in the model. And what I'm going to do is use the same function that we have here, where we generated our first input sensitivity. And now I'm going to generate our own simulation cases, okay? Or new simulation cases with these sensitivities, right? So now this is going to call, let's call it a fractional factorial, and this is low resolution, and this is dot data. And what I want to use is this scale matrix. The file is the same, which is a parameterized file, and the path is the same. Now we have new file prefix, new file suffix. So this is the beautiful thing of this is I run this, bang, immediately I have my new simulation cases. So if I go to the folder, we have there our 15 cases. And if I go there into case 0, I have my 0.001, and in some cases I have 1. 0.001, and in some other cases I have full connectivity. And I can check other files like case number 9. And I believe what's happening here. And this case is one here. So if you see the difference, let me put this in here like this. You see the difference now. So now we're changing. Sorry, so the ice cream trolley or van. And now we're changing the transmit. We are generating a lot of files. Again, what we would do is submit the files to the simulation case. Our file it's ready. I can keep submitting more files, but this is going to take a bit of time. And I have already some files, some solutions generated for this case. Okay. So before we go and do something else, before I move into another scenario, I want to show you that beyond the possibility of generating with experimental design, you can also use a bit of Monte Carlo. Okay, and inside this tool there is a lighting hypercube sampling. A lighting hypercube sampling. It's a kind of a more optimized way to sort of use a Monte Carlo and ensuring that that it's not completely random and you have an almost an even distribution of your variables in this multidimensional space. Let's say, because I say multidimensional because you have 14 variables, yes, and you want to explore the combination of low, mid, and high. In this case, you're trying just low, mid, and high. But let's see. Let's think that perhaps you want to try scenarios where you have just intermediate values and not only low, mid, and high. So for that, let's say we're going to try. Let's try Latin hypercube sampling. I think it's a Latin hypercube sampling. increase the number of cases. Okay, so let's go to the same steps. First step, it's generate the scenario. So I'm gonna call it DOE, Latin Hypercube Sampling, and this is 1, and this is pi DOE, and I believe that this is Latin Hypercube Sampling. So if I go to the documentation, I need to provide the number of samples, the number of cases, and how many samples I want. Let's say I want, I'm going to provide the number of features, and in this case, I'm going to generate a number of samples that I specifically want. I want to generate 60 cases. And like before, let's store this in a data frame with the same name or similar name, pd.dataframe with this name. We want to apply now, the columns are all variables, and we want to apply the scalar straight away. Let's apply a scalar straight away. I'm going to apply the scalar here, here, and here. So let's see what we have in there. The FDOE is not defined. Sorry, this is DOE. There we go. Now we have more or less intermediate values. Yes, we have 0.2, but we also have 0.02, and it's not all 0.1 to the minus 4 to 1, but I have some intermediate values that I can test. Okay, so let's say that at the beginning you finish with this experiment, and then you want to enhance the quality of your sensitivity analysis. Then you add a bit more of the scenarios. And now we want to export these scenarios. Let's put here just a header. And just one thing, and if you notice these in these cases, every time I run, can you see that the numbers are changing? The number changes. So if you don't want the numbers to change, when you generate the Latin Hypercube sampling, you need to put a random state and just fix a number. Doesn't matter which number you fix. 1, 1000, it doesn't matter. Just put a number so that when you run it, you always have the same output. And that's very important, because if you don't put that, you generate your cases. When you finish, you're going to realize that your simulation cases, you cannot reproduce your simulation cases. Okay, that's all fine. And now I have an alternative model, and I'm going to generate more models, and I'm going to call these models Latin Hypercube Sampling _ data. And again, just clicking running, and that's it. All the cases are generated. Now I have the Latin Hypercube sampling. And only 15. That's very weird. That's very weird. We have many more than 15 here. Oh, sorry. I need to replace the data frame, the output data frame, with the output, the Latin Hypercube sampling. So you see this here on this side. There you go. You have all the cases here. And now if we see again the file, you can see the difference here. Huh? We have some intermediate values and not only the extremes. So any questions so far? So, okay, so I'm going to call this file a simulation generator. Let's call it like that. And now let's go to the last bit of the exercise, which is the objective function calculation.